two quantities are related, you know the rate of change of one quantity, you are looking for the rate of change of other quantity. Okay. I will do the solution to question 1, and then you do question 2. If I don't feel comfortable, I could give you more questions to try. Okay. But keep in mind, all the variables, all the unknowns, x, y, and z are functions of t. Okay. When differentiating, everything is should be differentiated with respect to time t. I will go over question 1. Okay. Now question 1. For this kind of the problems, we prefer actually you have to use the Leibniz notation, the D notation. Okay. Now let's recall the meaning of this D notation. Dy over dt, it means the derivative of y with respect to t. Okay. For question 1, I'm going to write the steps in some details. Okay. Now the first thing we do is to differentiate the equation. With respect to time t, with respect to t, with respect to. So can I just write a t in here? You imagine t as a time. Okay, everything is changing in terms of time t. Every quantity is a function of t. It makes sense, right? Everything is changing in terms of time t, of course. Okay. And treating everything as a function of t, treating x and y as functions of t. So maybe I'm going to write one more sentence. Treating x and y as functions of t. After the topic implicit differentiation, I hope so this is easy to do. Okay. The equation is the underlined. Okay, we differentiated the underlined equation with respect to time t, term by term. Okay, term by term, everything is a function of t. In particular, x and y are functions of t. Okay, the derivative of x squared with respect to x, I think you have 2x. You have 2x using the power rule. But so do not forget we are differentiating with respect to time t. X is a function of t. Okay, you need to follow that by using the notation we used before by x prime. But I told you we prefer to use the Leibniz notation. You need to follow that by the derivative of x with respect to t. You could imagine it's x prime, but x prime, the notation, you do not know x prime is with respect to what. So because t is not introduced, so in the question, I mean t is implicit in question 1. Okay, so that's why I prefer to use the notation dy over dt. It means the derivative of x with respect to t. Okay, and then likewise we differentiate the second term. So we have using the power rule again, we differentiate 8y cubed with respect to y first, and then y is a function of t. Okay, so you have 24 times y squared. That's the derivative of 8y cubed. After differentiating that, y is a function of t. You need to follow that by dy over dt. Okay, it's kind of the same as before. So just we are using the Leibniz notation. The rule of thumb is right after you differentiate a function of x, you follow that by dx over dt. After you differentiate a function of y, you follow that by dy over dt. Okay, the same as before. Okay, differentiating the right hand side, you treat the right hand side 1 as a constant function of t. Okay, so the right hand side is equal to 0. That is the first step. Differentiate the equation with respect to time t. Okay. treating all the variables as functions of t. After that, all we need is to plug in the numbers. Again, we know the rate of change of x, so which is -3, and we are looking for the rate of change of y. Of course, you need to use other conditions. You just imagine other conditions is trying to describe an instant. Okay, we're looking for an instantaneous rate of change of y. If we know the instantaneous rate of change of x. Okay, the second step. It's always the case differentiating the equation first, and then we plug in the numbers. Okay. Plug all the conditions, so like dx over dt equals -3, and x value of 3 and the y value of -1 into the above equation. We have, wherever you see x value, you replace x with 3. Okay, so you just have 2 times 3. Can you start to denote a multiplication? Okay, 2 times 3. Okay, and then dx over dt, again you interpret that as the rate of change of x. The rate of change of x is given, it's -3, right? And then plus 24 times y squared, and y value is -1. Okay, yeah, y value is 91, so 91 the whole thing squared, it's y squared. Wherever you see y, you replace y with -1. Okay, and then dy over dt is equal to 0. Now I think you can see you can solve the equation for dy over dt. The only unknown number is the rate of change of y with respect to t. Okay, in the future you do not even have to say with respect to t, it's just the rate of change of y. Okay, very shortly after we do some word problems, the meaning will be clear. If you know the meaning of y, then you have a better way to interpret it. So dy over dt is a rate of change. Okay, but at this point we just solve the equation for dy over dt. I think the final answer, so maybe I'm not going to run too fast. So you have 24. You kind of isolate the rate of change of y. Okay, 24 times the rate of change of y is equal to, so be careful, this 91 the whole thing squared is positive 1. Okay, you move the other term to the other side of the equation. So do you have 18? I think you have 18. Okay, you have positive 18 if you move to the other side of the equation. Okay, now we are ready to solve the equation for the rate of change of y. Again, it represents an instantaneous rate of change, the derivative of y with respect to t, the instantaneous rate of change. The instance is given by when x value is 3, when y value is 91, and so on. Okay, I believe the answer is given by 18 over 24 simplified to 3 over 4. Is that right? I think 3 over 4 is right. So any questions about this? Again, when you see an equation like this, you treat all the variables as are functions of t. Essentially, we are doing implicit differentiation with respect to t. Okay, you treat everything as changing in terms of t. You differentiate all the terms with respect to t. The rule of thumb: after differentiating a function of x, you follow that by dx over dt. So because we treat x as a function of t, right? The same is true for a term or a function of y. After differentiating a function of y with respect to y, follow that by dy over dt. Okay. So that's the rule of thumb. Any questions? If you don't have any questions, try question number 2, please. Try question number 2, please. Another simple question. I will give you probably 1 or 2 minutes. 2 minutes, okay? To do the first step only. Differentiate the equation with respect to t, treating x and y as functions of t. Okay. Differentiate the equation with respect to t, treating x and y as functions of t. I think it's not too hard to write in the chat message. After you're done, you could tell me the answer, and then we compare the answers. It's probably a little bit long for you to write. The left hand side is y. Differentiate y with respect to y first. It's 1, and then follow that by dy over dt, the derivative of y with respect to t. Okay. So do not write y prime. And then for the right hand side, the same thing. You differentiate x cubed with respect to x. You have 3x squared, right? Do not stop here. X is a function of t. We're differentiating the equation with respect to t. You follow that by dx over dt. And then interpret dy over dt as a rate of change of y. The rate of change of y. Okay. And then you interpret dx over dt as the rate of change of x. Okay. The rate of change of x. That is the first step. You see, x and y, you imagine the two quantities x and y are related by an equation y equals x cubed. And then you are given the rate of change of y, so which is 3 units per second. And of course, you do not have to use seconds. Okay, if you are driving a car, it could be kilometers per hour or miles per hour, or whatever, right? Anyway, that is the first step. After we do the word problems, everything will be clear. You are going to see the meanings of the rate of change way better. Okay. Now the second step, we plug in the numbers. Wherever you see dy over dt, you replace dy over dt, the rate of change of y, with 3. And then wherever you see x, you replace x with 4. I think the left hand side you have 3. And then the right hand side you have 3 times x squared. You have 3 times 4 squared. Okay. And then solve the equation for the rate of change of x. I think it's 1 over 16. Any questions about this? I know you need to do you need the next stage after we do some word problems to fully understand what we mean by the related rates problem. Okay. Okay. Okay, now we're talking about a word problem. A word problem now. Okay. Again, in the future, almost in almost all the cases, any related rate problem is a word problem. Okay, if you like it or hate it, you are going to like it or hate it. Sorry, I don't know what I'm saying. I know some people like word problems, some people hate word problems. Actually, you could keep the handout open. On the handout, you have all the step procedures showing you how to do a question like this. But in the past, I realized so many people do not bother to follow the steps. So that's why for the assignment, the format of the questions are going to be the following. I gave you the step procedures I want you to follow. It's going to be something like this. I will show you the meanings of all the steps one by one. It's essentially the step procedures. Okay. For this one, it's probably easier if I switch the two screens, showing you the step procedures and then the meaning and everything. Okay. So probably before that, I'm going to write a slogan. Okay. Copy this on your notes. The derivatives describe rates of change. We have seen the idea too many times already. Okay. Now, for instance, the velocity describes how fast the displacement changes, right? It means at what rate the displacement changes. Now, for instance, the acceleration is the rate of change of the velocity. It means at what rate the velocity changes, right? Actually, we're going to see many other rates of change. Wherever you have a function of t, you differentiate the function, you have a rate of change. Okay. The first question is kind of on the harder side, but it will show you the meaning. I do want to include one question that has all the components I want to include first. Okay. The question is kind of a little bit on harder side, but it has all the components I want to include. So that's why I really want to include that question as the first one. In most cases, I'm trying to use the simplest ones as the first few questions, and they'll go harder and harder. But this one is kind of different. Okay. And by the way, we have started applications of differentiation applications. It's kind of, although it's in chapter 3, but we have started applications. We're kind of done the techniques. Okay, we'll follow the steps A, B, C, D, and so on. I don't need that. I don't need that either. In step A, we draw a sketch for the problem. You imagine you blow up the balloon at a constant rate of 100 cube centimeters per second. Okay. Now, you see when the volume is increasing at a constant rate, the diameter of the balloon also increases, right? Now try to follow me, try to understand me. You imagine you blow up the balloon. The volume of the balloon increases at a constant rate of 100 cube centimeters per second. Okay. And then the radius is increasing, the diameter is increasing, right? And then in the question we are looking for a rate of change. Try to understand that. the rate of change, it means how fast the diameter is increasing. It's actually an instantaneous rate of change when the diameter is 50 centimeters long. Okay. To help you understand the problem, so maybe try to answer my following question. Think, so before you answer, okay, try to imagine if the volume of the balloon increases at a constant rate, you imagine in the ideal case the balloon is a sphere shape, right? If the volume of the balloon increases at a constant rate, so now let's say 100 cubic centimeters per second. Listen to my question, okay? My question is, does the diameter increase at a constant rate? You just imagine you blow up the balloon with a pump, so electric pump maybe, okay, at a constant rate. The volume increases at a constant rate. And then my question was, does the diameter increase at a constant rate? You just imagine two special cases, okay? When the balloon is very tiny, you imagine the diameter, okay? So does it go faster than when the diameter is very large? I'm trying to say the volume of the balloon increases at a constant rate, and then the diameter increases at a slower and slower rate. When the balloon is very tiny, it goes very fast, right? Increases very fast. And then when the balloon gets larger and larger, the diameter, so does that make sense? The diameter increases slower and slower. It means the rate of change is slower and slower. So, sorry, the right answer is no. Okay. You're going to be convinced. If the volume increases at a constant rate, the diameter is increasing slower and slower. When the balloon is very large, the diameter increases at a very slow rate. Okay, I will convince you. Okay. Anyway, we go back to the problem. Okay, we follow the steps. We always follow the same steps. Okay. Now step A, we draw a sketch. For this question, it's simple. We draw a sketch, right? You draw a balloon, a sphere, so something like this. Okay. Right, then step A, draw a sketch. Okay. And then we move on to step B. Okay, now identify the quantities. Identify two quantities. So maybe try to answer my question. Okay. For which quantity we are given the rate of change? For which quantity are we given the rate of change? So tell me a word. For which quantity we are given the rate of change? The volume of the balloon increases at a rate of 100. The volume is right here. Okay, and then for which quantity are we looking for the rate of change? We are given the volume increases at a rate of 100 cube centimeters per second. It has to be in cube centimeters per second, right? And then for what quantity we are looking for the rate of change? You read the question. The question is how fast the diameter of the balloon increasing for the diameter. Yeah, that's right. Okay. And then in step B, okay. So because you told me earlier, the volume increases. You're given the rate of change of the volume, and we are looking for the rate of change of the diameter. Okay. Now we are going to use some letters to denote the two variables. Okay. I hope It's not hard to to understand the volume is a function of t. It's increasing with respect to time t, right? And the diameter also changes in terms of t. I mean, the volume can be treated as a function of t. The diameter is also a function of t in terms of t. I mean, okay. So we're going to use two notations, two letters to denote the two quantities. One quantity is the quantity for which we were given the rate of change. So the other quantity is the quantity for which we are looking for the rate of change. Okay. Anybody want to suggest a notation for the volume? You know what to use for the volume, right? Now let V be the volume. Actually, instead B, we introduce the notations. Okay, for the quantities. Instead B, I'm going back to this. Identify the quantity for which the rate of change is given. That is the volume. Okay, and also identify the quantity for which the rate of change is to be found. That is the diameter. I mean, the something's going on with Teams. So can you guys still hear me and see the screen? Can somebody confirm you can? Sure, thank you. Cool. Okay. Yeah, identify the quantity for which the rate of change is to be found. That is the diameter, right? And then we are going to use the variable notations to denote the quantities. By that I mean we are going to introduce two letters to represent the two quantities. Okay. Now let V be the volume, and it's kind of weird. I do not want to use D to denote the diameter. I know it's a commonly used notation, but still remember I told you we're going to use the Leibniz notation to denote the rate of change. The reason I do not use D is it's because I do not like this notation. This notation is ugly. Nobody use that notation. Okay, I'm just trying to say DD notation is ugly. Okay, I'm going to use X for the diameter for the diameter. Okay, and let X be the diameter. It's related rates problem. You know the volume and the diameter are related, but so there's no formula, no geometry formula that relates V and X. I'm trying to say the volume of the the sphere is not given in terms of the diameter. Instead, we have a formula to give the volume in terms of the radius of the sphere. I'm trying to say in order to get the relation between V and X, eventually we are going to relate V and X. But in order to achieve that, we need an intermediate quantity, that is the radius. By that we mean we have a handy formula to give a relation between V and the radius. Okay, and we also know a relation between the radius and the diameter. In this case, we need one other quantity. Okay, the radius. We also let, so now let's say R be the radius, of the balloon. You're going to see what's going on. Okay. Again, eventually we want a relation between V and X, the volume and the diameter. But in order to get that, we need the radius. That's what I'm trying to say. Okay. Now step C. Any questions so far? Simple, right? Just identify the quantity for which the rate of change is given, and also identify the quantity for which the rate of change is to be found. Introduce the variables. Okay. And then in step C, we're going to represent the given rate of change and the rate of change so to be found using the derivatives. Okay. Remember I told you if a quantity is a function of t, then the derivative of the function, it means the rate of change. Okay. In step C, what are we given? You read the question, okay? You look at that again. We are given the balloon, the volume of the balloon increases at a rate of, let's say, 100 cube centimeters per second. That's a rate of change. I do not want you to say that in words. I know the problem is a word problem. I want you to represent that 100 cube centimeters per second in terms of a derivative. That's a constant rate of change. Anybody want to tell me a notation representing that 100 cube centimeters per second? I'm looking for the left hand side. On the left hand side, what thing do you want to use to denote 100 cube centimeters per second? It's the rate of change of the volume. Now the problem is how to represent the rate of change of the volume using Leibniz notation. Okay, so that makes sense. I told you the derivative of v with respect to t is the rate of change, right? We're using the derivative dv over dt to denote the rate of change of the volume. It's a constant rate of change. Okay. That's the given rate of change. What are we looking for? So what do we want? What do we want? What do we want? So please try to write something in the chat message, please. What do we want? We are looking for, you look at the mouse cursor, how fast the diameter of the balloon increasing when the diameter is 50 centimeters long. Okay. We want a rate of change. We want the rate of change of the diameter, right? So we want dx over dt. We want dx over dt. It's because that's not a constant rate of change. I will convince you later, okay? We're going to see dx over dt is dependent on the time t. Okay, it's actually an instantaneous rate of change. Okay, now look at the last sentence in more details. Okay, we're looking for the instantaneous rate of change of the diameter, right? When the diameter is 50 centimeters long, it's an instantaneous rate of change. Okay, we want dx over dt, the rate of change of x, the rate of change of the diameter when the diameter is 50 centimeters long, when x is equal to 50 centimeters. Okay, so we're done step C. Should I summarize a little bit now? So because we are going to switch to move on to the next slide, I want to summarize a little bit. In step A, you draw a sketch. Okay, you draw a balloon. You imagine it's a 3D balloon. Okay, 3-dimensional. So if you want, you can write something like this to make it more 3D-ish. And then in second B, in step B, we want to introduce the variables to denote the quantities. Okay, at least introduce two unknowns, two variables. One variable is for the quantity for which you are given the rate of change, and the other variable to denote the quantity for which you are looking for the rate of change. Okay. But later on, we're going to get a relation between v and x. So that's why we need to introduce one other r in here. So because we have a handy formula for the volume of the balloon in terms of the radius, and we also know the relations between the radius and the diameter, right? For many of you guys, the next step is actually the hardest part. Okay. In this step, you need to recall many formulas. In many cases, you need to recall. I don't know what I did. Some formulas from geometry, from physics, from whatever other things. But so do not worry too much about the final. For the final, I will tell you what formulas to memorize. Okay. Are we on step D? The first thing in step D, okay, I will show you the wording. Okay. In step D, we are looking for an equation that can relate the two quantities. One quantity in this particular case is the volume V. So because we know the rate of change of V, and the other quantity is x, the diameter. So because we are looking for the rate of change of x. Okay. Now we are looking for the relations. You could search the internet. So probably you learned the formula a long time ago. Junior high school, the volume of a sphere. So do you remember that? At this point, try to get as many relations as possible. Okay. The volume V. I'm pretty sure you learned that in junior high school. The volume of the balloon, the sphere, right? Is 4/3 times pi r cubed in terms of the radius. So that's why we want to introduce the radius. Can you remember this? Yes. If you don't remember this, so try to remember it now. Okay. So that's the volume formula for a sphere or a ball. Okay. Again, eventually we need a relation between v and x. Okay. So anybody want to tell me a relation between r and x? So maybe r equals, r is the radius, x is the diameter. So do not lose track of the meaning. Again, v is the volume, r is the radius, x is the diameter. So do not lose track of the meaning. Eventually we want a relation between v and x, but in order to achieve that, we need a relation between v and r, and also r and x. It's half of x, right? In order to get the final relation, the first thing you do is to get as many relations as possible. Okay? And then we can use that to get the relations between v and x. Now see, in order to get a relations between v and x, all we need is to plug r value of half of x into the formula for v. So can I label the first using equation number 1, the second one using 2. Okay. Now we plug r value of let's say x over 2 into equation 1. Again, so because we know the rate of change of v is 100 cubic centimeters per second, right? And it's because we are looking for the rate of change of x. Eventually, we want a relation between v and x. Okay. Into equation 1, we have v equals r cubed. Now you replace r with x over 2. Now the whole thing cubed. Okay. the next thing we do is to differentiate the equation with respect to time t. So, but in order it's easier to do that, I think you have seen it before. We want to get a little bit more organized. We want to write the relation in some nicer form. Okay, I will show you what's going on. Okay, this equation is equivalent to v is equal to 4 over 3. You copy 4 over 3 and then times pi, right? And then x over 2, the whole thing cubed. The whole thing cubed can be written as x cubed over 2 cubed. So which is x cubed over 8. My scratch paper is here, okay? I'm trying to say x over 2, the whole thing cubed. Now you write that as x cubed over 8. So do you see what's going on? Again, the reason I do that is to get a little bit more organized, so that it's easier to differentiate the equation with respect to t. It will happen in next step. Okay. Simplify a little bit. We have the final relation we want. We have v is equal to, you see you cancel out 4 from the numerator and the denominator. On denominator you have 2, on numerator you have 1, right? And then we put all the constants all together. So do you have 1 over 6 and then times x cubed? I think I got this right. I forgot pi. Sorry, I forgot pi. 1 over 6 pi times x cubed. Again, pi is a constant, 6 constant, right? I'm putting all the constants together and put the variables all together. That's the final relation I want. So do you know what I mean? I want to repeat that. Okay, we know the rate of change of v. It's 100 cubic centimeters per second, and we are looking for the rate of change of x. We are looking for the rate of change of the radius, the diameter. I mean, sorry, the diameter. We are looking for the rate of change of the diameter. Okay, that's why I need a relation between b and x. You see, it's a related rates problem, right? Two quantities are related, v and x are related, volume and diameter are related, right? You know the rate of change of one quantity, you know the rate of change of the volume. You are looking for the rate of change of the other quantity. You are looking for the rate of change of the diameter, right? Related rates problem. Okay. So does that make sense? So the problem, now the word problem is converted to a math problem, a pure math problem. So do you see the problem is converted to the problem we did in part 1? Converted to that type of the problem now? Right. In most cases, step D is the longest step. Okay. But essentially it's junior high school or high school math. You just need to recall some geometry formulas and stuff. Okay. Any questions so far? If you don't have any questions, we'll move on to question E. Okay. In order to, now you have the relations between the two quantities. Now, after that, you need to have a relation between the rates of change, right? In order to achieve that, you need to differentiate the equation. Everything is a function of t. You need to differentiate the equation with respect to t. That's step E. Now in step E, differentiate the equation with respect to t. Differentiate the left hand side. So differentiate the v. So with respect to v first, you have 1, right? And then after differentiating a function of v, follow that by dv over dt. Okay, the same is true for the right hand side. Equals pi over 6, right? Leave out the constant. Pi over 6 is nothing but a constant. It's comparable to 2, to 2, to 3, to 5, the same thing. And then differentiate x cubed. The derivative of x cubed with respect to x is 3x squared. We write that as 3x squared. So do not stop here. Do not stop here. X is a function of t. Now we're differentiating with respect to t. Okay. Follow that by the rate of change of x. As I say, the rate of change of x. So just try to get used to dx over dt. It means the rate of change of x. Okay. I don't know you want to organize a little bit more or not, but this thing is actually the same thing as dv over dt. So the rate of change of the volume is equal to 3 and 6. You cancel out a factor of 3 from the numerator and the denominator. So that's what I meant. Okay. I think you are going to see half pi, right? X squared. The rate of change of x. Okay. Now we are ready to solve for the unknown rate of change. Now let's recall we are given the rate of change of v 100 cube centimeters per second. We are looking for the rate of change of x. So probably that's why I wanted to do step number C. Okay. So do you see dv over dt is 100, and we are looking for dx over dt, and then when the radius, when the diameter is 50 centimeters long, use all these conditions. You just remember two numbers. The rate of change of v is 100 cube centimeters per second, and then x value is 50. It's an instantaneous rate of change. Okay. All right. Should I forgot the step procedures. Yeah, now we're on step F. So plug in the given rate of change and the other conditions. By other conditions, I mean when x value is 50 centimeters long. Okay, again it's an instantaneous rate of change. And solve for the unknown rate of change. I'll show you the meaning. Now we move on to step F. Okay. By that I mean we plug. I think I can remember the numbers. The rate of change of v is 100 cube centimeters per second, right? So do you know why I use cube centimeters per second? It means the rate of change of the volume. Of course, the volume is in cube centimeters. So that makes sense. And the x value of we are looking for the instantaneous rate of change when the diameter is 50 centimeters long, right? X value is 50 centimeters, right? Plug the two conditions into that equation. Okay, the above equation. We have dv over dt. The rate of change of the volume is constant, so it is 100. In the equation, you do not have to include the units. Okay, it's equal to half pi, and then x squared. You know the value of x, so it is 50, right? So times 50 squared, and then isolate dx over dt. Now you see the only unknown thing is the thing you are looking for. I mean, the only unknown thing is the rate of change of the diameter we are looking for. Okay, so the diameter. The diameter I have this question in the course manual. I just copy a number from the course manual. It's 2/25 pi. Okay. Simple to solve for that. I think pi is on denominator, right? Come on. So anybody want to tell me the unit for dx over dt? The rate of change of x? The rate of change of v, the volume, should be in cube centimeters per second, right? If the volume is in cube centimeters per second, x, the diameter, is a one-dimensional stuff. Anybody want to tell me the unit? Centimeters per second. The rate of change is centimeters per second. Thank you. Okay. It's comparable to to the velocity, meters per second, right? Whatever, so kilometers per hour, right? The rate of change is some units per time. So that makes sense. Okay, so we're done step F. There's one more step. It's always the case for any word problem. The final thing you do is to answer question in words. Okay, answer question in words. Now I'm going to do the last step. Okay, in item number G, we answer question in word. To answer the question in word, so you have in words. I mean, you have to look at the question. You look at the question in here. The question we're trying to answer is how fast the diameter of the balloon increasing when the diameter is 50 centimeters long, right? Answer that question, okay? To answer how fast, or I could give the question something like, at what rate the diameter is increasing when the diameter is 50 centimeters long. How fast, it means at what rate. So that makes sense? Answer question, please. Okay. So maybe the diameter is increasing. I wrote it's increasing to indicate it's actually an instantaneous rate of change. Okay, it's increasing at a rate. So maybe at the rate of, forgot this number already, 2/25 pi. Centimeters per second. When, again, I want to repeat, it's an instantaneous rate of change. Okay. When the diameter is 50 centimeters long. Okay. Actually, question 2 is very similar to question 1. Simpler. I told you I would start from a harder question. So question 2 is simpler. Okay. It's a two-dimensional thing. It's a circle. Okay. Now you read the question. Okay. We know the rate of change of the area of a circle is decreasing at a constant rate. You just imagine you have a drop of water. Okay. When it dries, the area decreases at a constant rate. Now the question is how fast the diameter decreasing. It's an instantaneous rate, okay, when the diameter is 20 centimeters long. Okay. So because the question is very similar, I'm going to go over this a little bit quicker. Okay. few steps. Step A, you draw a sketch, a circle, right? Now step B, again, identify the quantity for which you are given the rate of change as the area of the circle, and also identify the quantity for which you are looking for the rate of change. It's the diameter of the circle, right? So you need to introduce at least two variables. Okay, one variable is to represent the area, so the other one is to represent the diameter. Okay. So maybe let A be the area, and X be the radius. I mean the diameter. Okay, sorry, diameter. So because you are looking for the rate of change for the diameter, right? But it's hard to get a relationship between the area and the diameter. What we know is how to get the area of a circle in terms of the radius. Okay, so that's why we need to introduce one other notation. Okay, so now let R be the radius. So we need three variables, okay, for three quantities. I mean, what are we given? We are given the rate of change of the area. Okay, given. It's kind of so important. So anybody want to tell me what are we given and what we want in terms of the derivative? What are we given, please, using a notation? What are we given in terms of the D notation? We are given the rate of change of the area, right? We use A to denote the area. So we are given the rate of change of A. So does that make sense? Sure, thank you. Yeah, dA over dt. So which is 10 square centimeters per second. So because the area is a two-dimensional thing, okay? The area, the unit is square centimeters per second. Okay. So what do we want? We want an instantaneous rate of change. So it is dx over dt, right? We want dx over dt. I mean the rate of change of the diameter. We read that in terms of dx over dt. Okay. Again, it's an instantaneous rate of change when the diameter, I mean when x, the diameter, is 20 centimeters long. So we're done step C. Now let's move on to D. Okay. So please, so maybe you can try to tell me something. Okay. How do you get as many relations as possible? At least you should know the area of a circle. How to write A, the area in terms of the radius? You know that. You know that. I'm pretty sure you know that. A equals the area of the circle pi r squared. You know that, right? And one other relation is the relations between x and x. Okay. I mean it's between r and x. R is the radius. X is the diameter. Okay. You know that the radius is half of the diameter. But eventually we want a relation between a and x. So because we know the rate of change of a, so it is 10 square centimeters per second, I guess, right? And then we are looking for the rate of change of x. Okay. So we have a relation between a and x as a equals pi times r squared. Wherever you see r, you replace r with half of x, the whole thing squared. Again, it's nothing but a equals pi r squared, right? Getting a little organized, so you have a equals. So maybe I'm going to write that in some more steps. Okay, so pi times x squared over 4. I was using x over 2, the whole thing squared is equal to x squared over 2 squared. Okay. You put all the constants so together, a is equal to pi over 4 and then times x squared. Right. That is the relation we want. We know the rate of change of a, right? We're looking for the rate of change of x. Sorry, I probably did something not too wrong, but a little bit wrong here. Okay. How to indicate the area of the circle decreases at a constant rate of 10 square centimeters per second. Sorry, I just remember that. In most cases, we use a negative number to denote it's decreasing. So that makes sense? A negative rate of change. Okay. I'm going to add a negative sign in here. Again, the area of the circle decreases at a constant rate of 10 centimeters per second. We use a negative number in here to denote the quantity is decreasing at some rate. So that makes sense? When the area decreases, the radius and the diameter decrease as well, right? Can I move on? So we're done step D. Okay. I believe in next step we need to differentiate the equations. That's one of the key steps. So maybe you try to tell me something. I know it's hard for you to write in the chat message, but you treat a as a function of t. You treat x as a function of t. You differentiate the equation with respect to time t. Okay, treating everything as a function of t. Okay. So on the left hand side you have the derivative of a with respect to t is the rate of change of a. Okay, the rate of change of the area. On the right hand side you have a constant, so it is pi over 4. Okay, you leave out the constant, so differentiate x squared with respect to t. Okay, so you have 2x, so which is the derivative of x squared with respect to x. So do not stop here. After differentiating a function of x, follow that by dx over dt, the same as before, right? Getting a little more organized. I believe you're going to have do you have half pi and then times x and then times dx over dt? Okay, I want to repeat something. Okay, the equation you get in step D is a equation that relates two quantities. One quantity is a, the area of the circle. The other quantity is x, the diameter of the circle, right? X is the diameter. Okay, and after differentiating the function, you have a relation between two rates. One is the rate of change of the area, so the other one is the rate of change of the diameter. Okay. And then we're almost ready to solve for unknown the rate of change. All we need is to use that equation. Okay. The last equation is the relation between the two rates, the rate of change of A, the rate of change of X. Okay. So do not lose track of the meaning. I think now we're on step F. In step F, I want to copy the relation between the two rates. Okay, we now plug the rate of change of A. I forgot the number already. It's -10. I think it's -10. -10 and 20. Okay. Into the above equation. We have dA over dt, so which is -10. Wherever you see dA, the rate of change of A, you replace that with -10, and then you have half pi, and then times x. X value is 20, right? And then you have the rate of change of x. So do you have dx over dt equals 1 over pi? On the right hand side, from the numerator and the denominator, you cancel out a 2, okay? So on numerator you have 10, right? And then from two sides of the equation, you divide two sides of the equation by 10 pi. I believe you have 1 over pi. Yeah, -1 over pi. Yeah, sorry about that. It's -1 over pi. So thank you. It's negative. Okay. It means the diameter is decreasing at that rate. So anybody want to tell me the unit for this one? The unit, please. That's the rate of change of the diameter. So which should be, diameter is one-dimensional stuff, right? It should be in centimeters per second. Okay. Sure, thank you. Centimeters per second, please. Centimeters per second. It's a rate of change. Okay, and then finally answer the question in words, please. Answer the question in words. The last step. Okay, you know how to answer the question. Okay. To complete the solution, I'm going to write the answer. Okay. G. I think G is the last step. Okay. You say something like the diameter decreases. It's decreasing at the rate of, I think, 1 over pi. If you say decreasing, you do not have to include the negative sign, right? The negative sign represents a quantity is decreasing at some rate. When, again, it's an instantaneous rate of change, okay? When the diameter is 20 centimeters long. We'll now look at another related rates problem. In step A, we draw a sketch. When drawing a sketch, we try to understand the problem. A plane is flying directly away from you, and you know the speed of the plane. That's a rate of change. the speed is 500 miles per hour, and the height of the plane is 3 miles. It means the plane is flying at the height of 3 miles. The question is how fast or at what rate is the angle of elevation changing at the moment when the plane is flying over the point on the ground 4 miles away from you. Now let's say if I'm using point A to denote the location of you stay at point A and observing the plane. I'm going to use point P to denote the location of the plane. Now let's say P is here. And the plane is flying away from you. The plane is flying to that direction. We also know the height of the plane, right? The height of the plane is 3 miles. Now let's say B is the point, so directly below the plane on the ground. Now let's say point B is here. P is the point on the ground, right below the plane. So that's point B. So we have a triangle. Now let's say AB. AB is the distance between where you stay, between you and the point on the ground right below the plane. And we also have the line segment PB. PB is the height of the plane, right? So PB is 3 miles. And if we connect A and P, we have a red triangle ABP. Now the angle of elevation is the angle A actually. Later on we are going to call this angle theta. I'm going to label the angle using theta. You can see as the plane flying further and further away from you, the angle theta is getting smaller and smaller. Now the question is, at what rate the angle of elevation changing at the moment when the plane is flying over a point on the ground? So now let's say when the line segment AB is 4 miles long, when the point right below the plane, this is point B, when AB is 4 miles long, right? Is the sketch in step A. Now in step B, we are going to introduce the variables representing the quantities for which we are given the rate of change and the quantities for which we are looking for the rate of change. So first of all, we identify the quantity for which we are given the rate of change. You look at the sentence, the first sentence. The speed of the planes is 500 miles per hour. It means the rate of change of point A, the distance, the rate of change of the distance between A and B. This distance is changing at the rate of 500 miles per hour. So we need to use a notation to represent AB. AB is the quantity, a changing quantity, right? For which we know the rate of change. And for what quantity are we looking for the rate of change? We are looking for the rate of change of the angle of elevation. By that we mean we are looking for at what rate the angle theta is changing when AB is 4 miles long. So we need to introduce at least two variables representing the two quantities. One quantity is the line segment AB. We know the rate of change of AB is 500 miles per hour. And we are looking for the rate of change of theta. So we let x be AB as shown. And we let theta be the angle of elevation. Now step C. In step C, we are trying to represent the given rate of change and the rate of change we are looking for in terms of the derivatives. What are we given? We are given the number 500 miles per hour. This is the rate of change of the distance between A and B. We are given the rate of change of x. We use x to denote the distance between A and B, right? We are given the rate of change of x. The value is 500 miles per hour. I'm going to write the full units. Okay. 500 miles per hour. That's a constant rate of change. Now the rate of change we are trying to find, the rate of change we are looking for, is the rate of change of the angle of elevation, d theta over dt. It means the rate of change of theta. You can imagine the rate of change of theta is not a constant. So now let's say when the plane is going further and further away, the rate of change of theta is getting smaller and smaller. So it's not a constant rate of change. We are looking for an instantaneous rate of change. When you look at the question, okay, we are looking for the rate of change of theta at the moment when the plane is flying over a pond on the ground 4 miles away from you. When x value is equal to 4, we're using AB to denote x. We're using x to denote AB, right? When x is equal to 4 miles. So we're done step C. Now step D. In step D, we get the relation between the two quantities. One quantity is x, for which we know the rate of change. The other quantity is the angle theta, for which we are looking for the rate of change. The relation is simple. Now let's say PB is the height at which the plane is flying. PB is 3 miles. And AB, we use x to denote AB, right? Now angle theta is the angle of elevation. We can see tan of theta, which is the opposite over adjacent. This will give you your equation between the angle and the x, theta and x, Now the relation between theta and x is given by tan of theta equals the opposite in that triangle, so which is 3 over x. In this question, we have only one relation between the two quantities. Now step E. In step E, we differentiate the equation with respect to time t. When differentiating, we treat theta as a function of t. We also treat x as a function of t. Right? We differentiate the equation with respect to time t. Now the left-hand side, the derivative of tan of theta with respect to theta is secant squared of theta. Secant of theta, the whole thing squared. So do not stop here. Theta is a function of t. We are differentiating the equation with respect to time t. Using the Chen rule, you need to follow that by the derivative of theta with respect to time t. That's the derivative of the left-hand side with respect to t. So likewise, differentiate the right-hand side. Now let's recall the derivative of 1 over x is equal to negative 1 over x squared. So the derivative of the right-hand side with respect to time t is equal to negative 3 over x squared. And then for the right-hand side, we are also differentiating the right-hand side with respect to t. So do not stop here. You need to follow that by the derivative of x with respect to t. The Chen rule, right? Now you look at the two equations in step D and in step E. The equation in step D gives you the relation between the angle of elevation and the distance of A and B, right? And after differentiating the equation with respect to time t, the equation in step E gives you a relation between the rate of change of theta and the rate of change of x is AB, at any moment, at any instant. I want to repeat, the equation in item number E gives you a relation between the two rates. One rate is the rate of change of theta, the other rate is the rate of change of x. So the two rates are related. This is the relation between the two rates at any moment, at any time. But in the question, we are looking for an instantaneous rate of change. We are looking for the rate of change of the angle theta and the rate of change of the angle of elevation, right? At the moment when the plane is flying over the point on the ground 4 miles away from you. By that we mean in the question we are looking for an instantaneous rate of change when x value is equal to 4 miles is equal to 4 miles. So we have seen that here, right? Now in step F. In step F, we are going to plug in the numbers. All the values are computed when at the moment when x value is equal to 4 miles. When x equals 4 miles, for the right hand side, you just replace x with 4. You just plug x value of 4 into the right hand side, and then the rate of change of x is equal to, let's recall, is the speed the plane is flying is 500 miles per hour. So this number is going to be 500. Okay, and the x value is 4 miles. Now all we need is to figure out secant squared of theta, which means secant of theta the whole thing squared when x value is 4 miles. We mean at that moment, what is the value of secant of theta the whole thing squared? When x value is 4 miles, we can use the right triangle to figure out the hypotenuse of the triangle when x value is 4 miles. Okay. Using the Pythagorean Theorem, it's easy to see the line segment AP, the line segment AP, it means the distance between the observer, which is u, and the plane, the distance between the 2 points. The hypotenuse of the triangle when x value is 4 miles equals square root of 4 squared and then plus 3 squared. You see the two legs are, the height is 3 miles and the x value when x is 4 miles, the distance between A and P is equal, it's computed using that formula, which is 5 miles. Now we are ready to figure out secant of theta the whole thing squared. So we'll do that a little slowly in 2 steps. Okay. You know secant of theta is 1 over cos of theta. We'll figure out cos of theta first. So we have cos of theta is equal to adjacent over hypotenuse. Again, we're trying to compute everything under the condition that when x value is 4 miles, adjacent is 4 and the hypotenuse is 5. Thus, we have secant of theta. Okay, secant of theta is the reciprocal of cos of theta. Which is 5 over 4 Now we are ready to plug everything into the equation in step E. Again, the equation in step E gives you a relation, the relation between the 2 rates of change. In the question, we are looking for an instantaneous rate of change when x value is 4 miles. But when x value is 4 miles, secant of theta is 5 over 4. Right? Now when x value is 4 miles, now we can plug everything into the equation. When x value is 4 miles, secant of theta is equal to 5 over 4. I'm going to replace that term with 5 over 4. Okay. 5 squared over 4 squared. That's secant of theta, the whole thing squared. And then d theta over dt, the rate of change of theta, equals negative 3 over x squared. 3 over x value is 4. Okay, everything is computed at the instant, at the moment when x value is 4. So you have 4 squared, right? And then dx over dt is the rate of change of x. It's the speed the plane is flying. You see it's 500 miles per hour. We just replace dx over dt with 500. That means this equation is equivalent to 5 squared, you have 25. On denominator, you have 16. And then the rate of change of theta equals negative 3 over 4 squared, which is 16, and then times 500. From this equation, it's easy to solve the equation for the rate of change of theta. Now all we need is to multiply two sides of the equation by 16 over 25. We multiply the left hand side and the right hand side by 16 over 25. By 16 over 25. You see 16 and 16 are cancelled, 25 and 25 are cancelled. On the left hand side, you just have d theta over dt, the rate of change of theta. And on the right hand side, you have negative 16 and 16 are cancelled, and the 500 divided by 25 is equal to 20. Then 3 times 20 is equal to 60. So d theta over dt is equal to negative 60. Now the unit for the rate of change of theta. In calculus, we always use radian measurements. We never use degree, unless otherwise specified. So the unit of the rate of change of theta is radians per second. I mean radians per hour. The time is in hours, right? The sign is negative. It makes sense. So because as the plane is flying further and further away from you, the angle of elevation you imagine is getting smaller and smaller. That's why we have a negative rate of change. Also, this number might be looking a little bit too big, but the measurement here is in radians per hour. 1 hour is long, right? In order for the number to make more sense, we're going to do some conversion. We're going to convert the unit to how many radians per second. In order to do that, all we need is to divide this number by 3600. So because there are 3600 seconds in an hour, this is equal to negative 60 over 3600. Now the unit is going to be in radians per second. Right. Using a calculator, we can round this number to 4 decimal places. The answer is 0.01667 if we round the number to 4 decimal places. I will specify how many decimal places I want for any assignment questions or the final questions. Okay. This is negative 0.0167 if we round the number to 4 decimal places. Now the unit is in radians per second, right? if at this point you still cannot imagine the rate of change, at what rate the angle of elevation is changing, we can convert the number further to how many degrees per second. In order to do that, now let's recall the relation between the radian measurement and the degree measurements. We mentioned before, the only formula you need to remember is pi radians is equal to 180 degrees. So 1 radian is equal to 180 degrees over pi. By that we mean, you look at here, this is the unit of this one as in radians per second. In order to convert this number to how many degrees per second, all we need is to multiply this number by 180 over pi. We multiply this number by negative 0.0167 times 180 over pi. Using your calculator, you can see this number times 180 over pi. This number is equal to 0.9568. The unit of this number is in degrees per second. I hope this value is easier to imagine. This means when x value is 4 miles, the angle of elevation is decreasing at slightly less than 1 degree per second. I think this number is making more sense. Finally, we need to answer the question in words, the last step. The angle of elevation is decreasing. It's because the value is negative at the rate of 0.9568 degrees per second when the plane is flying over the pond on the ground 4 miles from you.